Hello. This is a relatively short presentation on my understandings of the topics UML, test-driven development, and software security. Beginning first with UML. So what is UML? UML is short for Unified Modeling Language. It has been in use since 1997, although in 2005 the ISO adopted it as a standard. UML is useful for visually representing systems such as programs, computer hardware systems, and it can even be used to represent real-life situations. Why would you want to use UML? Well, UML is very useful when it comes to software development, and especially object-oriented programming. The basis of UML shows how various objects interact with each other. You can list methods and data that they manipulate. UML is also language independent, meaning it can be used across multiple programming languages. UML represents abstract design, so you don't need any syntax that is unique to one programming language or another. Since it is an ISO standard, there's also a good chance that many other software developers will be able to understand your UML diagrams. There are three key elements to UML: things and objects, the relationships that those objects share, and the types of diagrams that should be used. Here's an example of two objects. We have a person object and a book object. Both of these objects have names. Below those names, you'll find attributes. For example, the person object has a string variable name and a date variable birth date. The book object has a string variable title and a string array of the authors. We also have object methods. For example, person has a method that returns a string called getName. The method setName does not return a variable because it is a setter method, not a getter method. And the isBirthday method returns a Boolean, either true or false. The book object has a getTitle method, which returns a string, a getAuthors method, which returns an array of strings, and the addAuthor method, which presumably adds an author to that array. Each object in UML is displayed with the attributes, data types, and methods. When you have two or more objects, you have to show their relationship. Relationships are shown with lines and arrows. Association is shown with a solid line and a hollow arrow. Dependency is shown with a dashed line and a hollow arrow, and inheritance is shown with a solid line and a solid arrow. Relationships can be labeled with the specific interaction that happens between the two objects. Here we have two objects, a customer and a shoe. Typically, these objects would be labeled with their attributes as well as their methods, but for the sake of the example, we just have the object names. Say we wanted to show that customers purchase shoes. First, we would pick the type of association. So for this case, we are going to use the hollow arrow. Then we can label the interaction with purchases. Once you have your objects and relationships, it's time to pick an appropriate diagram. UML has many different diagrams that are each used for their own unique purpose. The most common diagrams include class diagrams, which shows elements of classes, like their methods and instances of them, and how they interact with one another. Use case diagrams, which show how programs will be used in real-life scenarios, and object diagrams, which shows elements of various objects. This is an example of a use case diagram. Here, we have the 4 subjects that will interact with the system. And inside of the system boundary, we have those interactions laid out. We can also see the relationships between the 4 subjects based on how they interact with things inside the system boundary. We have actions such as order food, which is done by both the waiter and the client. Actions like pay for food, which is done by the waiter, client, and the cashier. And we have dependencies such as serve wine, which depends on whether or not the client ordered it. Use case diagrams are especially helpful when you want to illustrate how subject interactions and actions overlap and intertwine. Now we're moving on to test-driven development. What is test-driven development? Test-driven development is a style of development that builds software using completed tests. First, an outline of code is written without any functional data. The program is meant to fail. You use unwritten methods, classes are used that are unfinished, and undefined variables are often manipulated. What this does is it creates a checklist. You have a clear starting point and a clear finish line. It may seem counterintuitive to write code that purposely fails. However, there are some advantages to this method of development. One, it's proven to increase productivity. It's also easier to work cooperatively because multiple people can be working on different tests at once. It limits redundancy, therefore limiting bugs. It also creates leaner code and thus easier to read code. In order to achieve all of these, TTD follows very particular steps. First, being constructing a test without any functional code. This is the start and the finish line. Then you have to run the test to ensure that it fails. Once you're sure that the test fails, you then define test code to try and pass the test. You then rerun the test to make sure that it is now successful. You then go through code revisions and then repeat. So here we have an example of a student class. We have the starting line, which is the class of student. We know that we have to write a student class. We have the finish line, which calls a method that is undefined in the student class. We now have a finish line that we are working towards. Here, we're going to work through a simple example. We want to create a student class that has the attributes first name, last name, grade level, and grade point average. And it needs to have the methods set grade level and set GPA. So for the first step, we're going to construct a failure test. As you can see, this test has no functional code, and it does indeed fail when it's ran. However, we have a starting point with the student class, and we have a finish line. We need to be able to create a new student object. We need to be able to set its grade level using a class method, and we need to be able to set the GPA using a method. So the next step is to add functional code. Here, we have defined the student class with attributes first name, last name, grade level, and grade point average. Following along to one of our goals, we can now create a student object. However, the methods still are not defined, and the program fails at the first line that calls a method. So in order to pass the test, we need to add just enough functional code to be able to run those methods successfully. Here, I have added just enough code to define those methods, and now the program works. At this point, you would make code revisions where necessary, and if this was part of a larger project, you would add this code and then move on to the next step, where you would repeat the process of writing a failing test in order to pass it later. You can see how using test-driven development to add just enough code to get the program to work keeps it lean, easy to read, would increase productivity, and reduces the amount of complicated code that could lead to bugs. Now we're moving on to the final topic, which is software security. Software security is important because it lets your users know that they can trust your program and trust their information in the hands of your program. In order to do this, it is important to consider three main points: exposure of data, the types of threats that your software may encounter, and controls that you can put in place to prevent any insecurities. Analyzing the exposure of certain data is important because it gives you a good idea of what data should be more protected than others. To do this, each asset should be evaluated based on the time it takes to replace and the amount of data that you would lose if you were to lose that asset. Obviously, assets with higher data costs and longer replacement times should be treated as having a higher level of exposure and thus a higher level of security. It is also important to recognize how assets might be attacked. Potential threats can attack in different ways, and data can be compromised. You need to analyze what data needs protection, going back to exposure analysis. Then, you need to put yourself in the shoes of the attacker. Think about how it will be attacked and what you can do to prevent those attacks. Attacks can come in the form of viruses, malware, ransomware, backdoors, and countless others. Now it's time to focus on controls. Controls are key in preventing attacks and mitigating damage. You need to ask yourself, what can you do to practically prevent these attacks? And how can the damage be mitigated? There are three important security policies that can really help in this situation. Those three are integrity, confidentiality, and multi-level security policies. Integrity policies tend to focus on maintaining data correctness. They prevent alteration of information, ensures that the data is displayed as originally intended, and keeps data away from non-genuine users. This way, users can trust that the data that they see is indeed the data that they were meant to see. Confidentiality policies focus on maintaining the privacy of information. Confidentiality policies only allow the reading of data by authorized individuals. This is very important when you are maintaining the security of personal files and databases. Multi-level security policies tend to integrate elements of both integrity and confidentiality policies. What multi-level does is it assigns classification values to both users and data, Only users with the same classification value or higher can read or write information to particular sets of data with the same classification value. This is typically implemented at governmental levels. These security policies can be realized with security tools. There are many security tools, but the most common today consist of public and private keys, sandboxing, and virtual machines. Public and private keys is when data is encoded with somebody's public key, then sent to them and can only be decoded with their private key. This ensures that there is no man in the middle that is able to access or alter the data in transit. Sandboxing is when processes are ran in an isolated environment, restricting access to other files. If there is an intrusion or a security compromise in a process, it does not go outside the sandbox. Similarly, virtual machines run everything in a virtual environment. So if there is a security compromise, nothing else on the user's personal machine is compromised because that compromised program is being run on a virtual machine